Hello. As you can see, our catalyst contains several different threads. This one is dedicated to the smart grid. And by smart grid, we are emphasizing a new approach to decentralizing electric power called fractal microgrids.
Here we see an example of the Agile fractal grid in action whilst we simulate an outage. Some areas lose power but can island themselves using combinations of backup power, distributed generation and stored energy. Smart control systems allow the islands to network, potentially allowing for some power to be restored in affected areas whilst the utility works to bring the dark areas back online. Soon, everyone is back on grid power as the microgrids reconnect with the utility.
As you can see from the animation, this is a distributed approach to resiliency. But to scale eventually to national coverage, the catalyst is introducing a four-tiered architecture. This can best be seen in this next diagram. Each of these microgrids can not only generate its own power, but each serves as a 5G picocell, each has an edge computing facility, and each is secure in its own enclave from the rest of the world. At Tier 1, we have the distributed microgrids. At Tier 2, we have redundant district operations controllers to balance the cluster. At Tier 3, we have the interfaces to all of the regional energy financial markets. At Tier 4, we have a place to watch, but not touch, everything that's happening across the country. At the top, we also have a digital twin continuous integration simulator. This is what we will use to launch the deployment of custom configured microgrids as fast as possible for every participating locale. As shown here in this stick figure skeleton, our four-tiered architecture is modeled on a standard approach for the catalyst. Each of the use cases for the power grid operates across several of the distributed nodes and interacts with the others. If any node breaks, the others recognize this fact and then just keep working in an islanded mode. The resilient 5G use case for the smart grid overlays our now familiar four-tiered architecture as shown in this diagram. At the microgrid on Tier 1 on the left, the various devices are now connected to a fault-tolerant microgrid controller with wired Ethernet connections. For resiliency, the Tier 1 fractal also poses as a 5G picocell at that location, and each device also connects to the microgrid controller with a 5G wireless connection. Both connections use the DDS protocol supporting low latency, real-time, redundant communications for high availability. The Open RAN control for the 5G network itself is back at the Tier 2 district node, supporting the entire district of picocells, regardless of whether they are fractals or not. For carrier participation, the Neutral Host Communications Access Service is controlled back at the cloud at Tier 3. The interconnection with the participating carrier's core is at a national location with that carrier at Tier 4. Because of the mission-critical nature of grid outages, we will use Stratus fault-tolerant edge nodes to control the microgrid operation. Both wired communications and wireless 5G communications need to be employed for redundancy so that the entire grid is more fault-tolerant. We will use the industrial internet DDS protocols that were born in the weapons industry and are now standard for the electric power industry in the US. Using the DDS fault-tolerant event signaling, the same messages flow over multiple paths, but at the receiving end, only one packet is actually used. Thus, there is never an interruption in the flow of processing, even if one of the nodes is physically destroyed. This is now part of the field message bus standard for the power grid in the United States. To keep the enormous chatter under control, the four tiers are isolated into separate domains to contain the flood of events in the publish and subscribe protocols. With this approach, only those events meant for upward or downward delivery traverse the inter-tier communications. This allows the entire nation to talk while ensuring that those important events that need to be heard can traverse to anyone who needs to be involved without flooding the channels unnecessarily. A good example of this enormous network traffic is that of the Synchrophasor, which is now the new darling of the electric grid itself. The Synchrophasor sensors are placed at the edge of the grid, measuring up to 6 electrical power metrics up to 120 times per second. The phaser data concentrators act as store and forward nodes, aggregating the measurements for communications efficiency. The measurements are stored as far into the network as possible to control the massive data traffic, but are summarized and forwarded to the upper tiers, to the dashboards where the human monitoring for balance of the national grid takes place. Human observation takes place at Tier 4, but analytics can reach all the way back down to Tier 2 for the distributed analytics purposes. Despite the size of the distributed national data store, the distribution of private clouds to the edge allows massive analysis inquiries in just moments. Another delightful aspect of decentralizing the power grid is that power can now be traded back and forth amongst the participants for the purposes of reduction of costs. This is best done during stressful moments when the power is otherwise quite expensive. In this use case, you have a variety of prosumers who each have the ability to generate their own power at their own homes or business locations, but they have the ability to share this power with their neighbors. Using the special IOTA distributed ledger style techniques can make the microtransactions quite fair, but also quite invisible to the average consumer. And simplicity is the watchword of the day for busy consumers. This architectural diagram shows the placement of active control components when one is using the fractal grids to trade power between prosumers in a neighborhood. This uses a distributed ledger called the Tangle to help all of the distributed parties keep track of the commitments and deliveries. A dialogue between the prosumers uses the classic commodity steps to consummate the trades and deliveries of the services. It's just like airline points that are traded as opposed to cash. Of course, you can always convert your power tokens to real cash using the Visa credit card system if you need to. But now the whole distributed system needs to be secure with the mischief that abounds in the world in which we live today. And it needs industrial operational technology styles of protection, not just office-related IT types of security that we're all accustomed to. The placement of OT security instrumentation in the microgrid is shown in this diagram. Because of the OT nature of the operation, an invisible forensic data collector, or an FDC, is placed in the appropriate point in the subnetwork in the microgrid yard to passively sniff all messages and behavior going on. Because of the size of the data collected, the data is stored at the edge, and then interesting events are forwarded upward through the tiers, until the most interesting ones reach the Security Operations Center where the monitoring of the service resides. If suspicious behavior is observed, it can be monitored and even stopped by the system. Where authorized, the distributed security system takes positive steps to recover and resume production operations where the damage has been suffered. The entire security operation runs in a closed-loop fashion. Emergency action, if pre-authorized, can take immediate action. And then, more thoughtful collaboration activities can suggest longer-term operational changes that can be simulated in the digital twin, and then fed back to the end environment through the DevSecOps processes for long-term control changes, using blue-green techniques so that the grid never needs to be stopped just for software updates. The following animation describes the gist of this new continuous integration technique.
A digital twin is a digital model of a physical asset which continuously collects information via sensors, public data or other IoT collection tools and applies advanced analytics, machine learning and artificial intelligence to gain valuable real-time insights about the physical asset's performance, operation or profitability. The intention is to use the digital twin not just for design but for the integration of hardware solutions, system testing, functionality certification, construction management and supporting production operations. The digital twin serves to synchronize the massive efforts of large numbers of people by providing an efficient and infinitely expandable framework for progress.
So this is the group that has collaborated to bring you these advances in the power grid. Please review the materials in the grab bag for this thread to see more details on what each participant has brought to the table. You may see some of these participants playing a role as cross-threads in other catalysts too. Thank you for being part of this very large and important movement on our common objective of controlling global climate change and also improving the availability, resiliency, and security of your electric power grid. Thank you very much.